All right, so let us talk about how we can induce bilingual embeddings. So first of all, we're going to discuss a naive approach, and then later on a couple of more sophisticated approaches. So a first naive approach would be, let's say we have already induced monolingual embeddings for, let's say our languages are English and German, and we have an English corpus, a big English corpus, and a big German corpus, and we induce monolingual embeddings from these corpora, one in English and one in German, and for example, we use Word2Vec for that. And then let's secondly assume we have a dictionary that maps between English words and between German words. Of course, our dictionary is finite, so maybe we have like 10,000 pairs of translations in that dictionary. Now, what we could do is we translate the German words to the English words, and then we assign them the embeddings of the English word, right? So let's say you have the German word Katze, and in our dictionary we look up the translation of Katze in English, which maybe is cat, and then we take the English word vector for cat, and we say this word vector is now the word vector of Katze, right? So then in this case, we would totally ignore our German embeddings. So we could also do a concatenation. Maybe we concatenate if we have Katze and cat. So maybe cat gets the English vector and the German vector, and Katze also gets the English vector and then the German vector concatenated or averaged, right? So we could do a couple of such things. And then the main limitation of that approach is, of course, the dictionary, because where do we get the dictionary from? So we kind of have to induce that. A dictionary, maybe for English and German, it's not so difficult, but there may be many other languages pairs where we cannot induce a dictionary. But on the other hand, just getting this dictionary is also not so complicated, but using this approach suggested by just assigning translation pairs the vectors from the other language is then of course limited by not being able to give words a vector that are not in the dictionary, right? So let's say we have our 10,000 pairs, and all other words that are not in the dictionary, they will not end up having any vector. So this is a naive approach. It's possible to do, but it has its clear limitations. So then the literature has suggested different approaches that are more complex and that we will see in the following. So one of the first and simplest approaches has already been proposed in 2013 by Thomas Mikolov is we have again the same situation as before. We have our monolingual embeddings for English and German. We have our dictionary. How does the dictionary look like? As I said, there are pairs in the dictionary like cat and Katze, table, tisch, and so on. And we can write these pairs in a table format where we have the English pairs xi paired up with the German words zi. So we have cat, Katze, table, tisch, and so on. And then, of course, because we have the monolingual embeddings, we have the embeddings for these words. So I write these embeddings now in bold font. I'm not sure if you can differentiate that, but before it was a normal font, now it's bold font. So these are vectors, and these are the vectors that we get from the monolingual embeddings. So now, what do we do with these monolingual embeddings and the vectors that we have? So we would estimate a linear transformation, and this linear transformation looks as follows. We want to estimate a matrix W such that if we take if we take a pair xi zi from our dictionary, right? So that's from xi and zi are from the dictionary, and then we use the vectors. So we use the vectors, the vector xi and the vector zi. Then we want to learn a transformation matrix such that if I multiply xi by w, then this transformation, so we take the English vectors and we transform them, and the transformed vector should be close to the German vector, right? And we want to minimize over all possible matrices, and we want to minimize the sum over all the words in our dictionary, right? And we use the standard like this is the Euclidean distance squared, right? So in this way we can transform the English embedding space to become similar to the German embedding space. And then once we have learned this W, we can map any language X word, so any English word, any new word that is not in our dictionary, can also be mapped into the space of the German language, right? So even if we do not have the dictionary. So this is really overcoming the limitations of the dictionary. So and then here is another question that I put in green here. So what does this equation here remind you of? If you have closely followed the lecture up to now, you will recognize something in this formula, and what you can recognize is, well, this actually looks like a neural network that has one hidden layer. So we have the input xi, we have one layer. Actually, it's not a hidden layer, so it has no hidden layer. It's like a perceptron. So we map xi, the input xi, we multiply that by the transformation matrix W. we get our neural network prediction. So there's nonlinearity here, no nonlinearity here. So this is just a linear activation function in the output layer, and then our target is the Zi. So we want to make our network predict the German embeddings, and we take here the square loss. No, this is the square loss, and we sum over all our data points in our dictionary, right? And we minimize over double. So this is a neural network without hidden layers. So it's a perceptron that we use to solve this minimization problem here. Good. So these bilingual and multilingual embeddings have been very popular. So many different approaches have been proposed. There are a couple of survey papers. There's more recent survey papers by Gore and Klavash from University of Mannheim, who is also talking about the evaluation of those cross-lingual embeddings. So that's a very readable paper. I recommend to have a look at this paper if you're interested in the topic of cross-linguality or multilinguality. But here in the following description, I will more talk about this older paper here from 2016, where they give where they outline 4 different approaches that had been proposed up to then, and we will check out 2 of these approaches. So they look at 4 different approaches. That's from the 2016 papers that have been proposed up to the point in time when the survey paper was published. The first one is called BiSkip. The second one BiCVN, BiCCA, and BiVCD. So these are the 4 approaches, and they compare these 4 approaches according to the information that they need. So they say this approach here needs most information signals, and this approach here uses least information signals, and as we go from A to D, the amount of information signals needed decreases. So which information signal does the first approach need? Well, it needs aligned pairs. So you have to know that I love you is the translation of the French sentence je t'aime. Not only does it have to have aligned sentences, so this is an aligned sentence. These are aligned sentences, but also the words in the sentence have to be aligned, right? So this is a strong assumption, and getting this information is kind of costly. We have to develop tools that are able of doing that. The second approach only assumes that we know the sentences are translations of each other without knowing which word belong to which. The third one only uses this dictionary, right? So we have a dictionary that is similar to the approach of Mikolov that we have just seen, right? So we need that dictionary. And the fourth approach, the last approach, it only needs aligned documents, right? You don't have to know. So there here are 2 sentences in French. and there are 3 sentences in English, so we don't have to know which sentence belongs to which. Neither do we have to know which word belongs to which. We only have to know these 2 documents are comparable documents that are kind of translations of each other. So we're going to discuss briefly method number A and method number D. So the by-skip approach, method number A, it uses sentence and word-aligned text, then runs a skipgram model whose contexts are words from both languages. So if the input love comes in, we would usually predict, if we were in a monolingual context, we would predict the 2 neighbors, one neighbor to the left, one neighbor to the right. So we would predict I and you, right? And now what by-skip is doing, it also predicts the translations of these neighbors. So it would also predict je and te, right? So it would, if left comes in, it predicts je, I, you, and te. And similarly for the French word aim, which is the translation of love, it would predict, it would predict te, and it would also predict the translation of te, which is you. So that's a modification it uses compared to the original monolingual word2vec. And what you can see now is, of course, first of all, the monolingual constraints are preserved, so it predicts the same context as in the monolingual case, but in addition it predicts some other context. So, but from the monolingual context being preserved, we hope to infer that this model is able to induce embeddings that satisfy this monolingual objective, namely that similar words in one language should be close to one another. And because for similar words like love and M, it also predicts similar contexts, namely, a little bit of French context and a little bit of English context, and for love it's the same, English and French. And you see that these contexts here are really overlapping. They are not identical. They are not identical, but they are really strongly overlapping. So we would also hope that from the second constraint, the model would also learn this cross-lingual objective, namely that cross-lingually similar words are close to each other in the vector space. And then we can try this model out, and indeed, if we would do respective tests, then we would see that the model indeed satisfies these conditions that we hope it would satisfy. Then the ByVCD, that is a very, very simple document. It's a very simple approach. So what it's doing is it's taking aligned documents, for example, a Wikipedia article on Donald Trump. So it takes the English Wikipedia article and a German Wikipedia article. Then it merges them and randomly shuffles all of the words. And then it runs a monolingual model. For example, take your favorite model, SIBO, GLOV, skipgram, whatever you have on this shuffled corpus. And then that's it, right? That's the model. Now the question is, does that give any meaningful results, and under which conditions? So, so the answer is yes, it does give meaningful results if the articles are comparable, right? If they are comparable in length, in general, and if they are similar articles. Let's take a simple case where the articles are translations of each other, like sentences that are translations of each other, like that's what we call parallel sentences, right? You have 1,000 English sentences and 1,000 German translations of these sentences. So sentences are rather short. Let's say they have like between 10 and 20 words. In reality, of course, it can be a little shorter and a little bit longer also, but let's say between 10 and 20 words. Then we would merge like on the order of like 30 words. We have 30 words. We merge them, randomly shuffle them, and apply word2vec, for example. So this actually is equivalent to just having a long like a long window in Word2Vec. So if Word2Vec has a window of like 30, it looks 30 to the right and 30 to the left for each word. And with such a long window, we would already be capturing our sentences. And the order doesn't matter anyway, because Word2Vec is kind of an order-free model, right? Like SIBO, in particularly, SIBO means um, contextual bag of words, right? It's contextual bag of words. It's a bag of words model. Bag of words means order plays no role. It's like a set, but with possibly multiple occurrences of elements in the set. So SIBO has no order, but also skipgram has no order, right? It just predicts the neighbors in any order. It doesn't matter which order they have. So at least all of these three models here are order insensitive. So it just means we would take a big Word2Vec model, like a standard Word2Vec model with a big window size, and would run it on our sentences, right? And typically, if you increase the window size in Word2Vec, it doesn't get so much worse the results, or like the results differ a little bit, and the outcoming vectors are a little bit different, but it doesn't have a devastating effect, right? And the order freeness also does not have a devastating effect. Word2Vec works well, even though it has this order freeness property. So, taken all together, we can imagine that in certain circumstances, this really does yield reasonable results. And also what's coming out is that words that are that are similar across languages, like am and love, so these are translations of each other, they would typically occur with a similar randomly shuffled context. And because they have similar randomly shuffled contexts, they would probably get vectors that are quite similar in nature, and thereby satisfying these two properties, namely, or satisfying the cross-lingual property that cross-lingually similar words also have similar vectors. So this is a very simple approach that works under certain circumstances, right? And the circumstances are, you have to have comparable articles, and maybe they should be rather short articles, like either sentences or like 2 or 3 sentences at most, right? They should not have thousands of sentences. And then another question is, where do we actually get the bilingual mappings from? So for this biskip model, we said we need these bilingual mappings. So we need to know that je and I are aligned, that love and am are aligned. So how do we know that these alignments hold? So where can we get them from? Either we have a dictionary, okay, that would be one option. Another option would be, but not that would not be a too good choice, because the dictionary is something static, and in the context of sentences, the meaning of words may change, and as is the basis for Elmo and Bird. So, a dictionary cannot capture that that contextual reshaping of meaning, right? Another thing is, like, we can go to Wikipedia and check the links between the languages. Like if you see the I don't know, the German word water, it may have a link. The German word Wasser, it may have a link to the English word. The English Wikipedia article for water, maybe, right? Or you just say, I want to have the definition of water in another language. Then you come to the English and the French, etc., etc. Wikipedia entries for Wasser. Or what is commonly used in natural language processing is that we learn these word alignments from parallel corpora. How does that look like? So, for example, one famous parallel corpus is the Europal, which holds the proceedings of the European Parliament. So the European Parliament is issuing well, it's proceedings, and these are translated in multiple different languages. So they are not only in one language, but in all of the languages of the European Union. And what it looks like is you can, for example, you have, let's say, you search for the, you search some English text in the Europal corpus, such as, also I would like to pay tribute to the clarity of the report, etc., etc. And then you will find the corresponding sentences in German, in French, in Spanish, and Italian, probably. So that's how it looks like. And then you have matched up sentences, and from these you can use unsupervised algorithms that work on certain principles that then automatically and unsupervisedly infer the alignments, right? So how that works is not the scope of this lecture, but basically you can think that if you have sentences that are very short, maybe just one word long, then you can already know the exact matchup. So if you would have a sentence that only consists of de and le, so you have an English sentence de and a French sentence le, you immediately know that de and le are kind of associated. And then from this you can infer to like longer sentences. So you iteratively infer from short sentences to long sentences, so to speak, right? And that's where we get these alignments from. So good. So we talked about mapping 2 languages in a common space. How about 3, 5, and 10 languages? So until like 2018 or so, this was a much less explored topic. And then only gradually over time, like starting with 2016, people started to work on more languages, right? For example, this work here, 2016, where they extended, for example, the bi-skip model to multi-skip and bi-CCA to multi-CCA. But starting with BERT, actually, so this is not a topic that is less explored anymore, because nowadays BERT exists as multilingual BERT, so-called MBERT, and this yields embeddings in a joint space for more than 100 languages. So this is really big nowadays. So we have more than 100 languages, and the embeddings are really in a cross-lingually joint space. Yeah, I will not go into the details of how multilingual BERT is doing that, but keep in mind that nowadays this well, we have this big opportunity of having BERT available in a shared joint space across approximately 100 languages. And then also another topic that came about in the last 2 to 3 years is people found, okay, these bilingual vector spaces are not so difficult, and we have techniques that allow for inducing good bilingual embeddings, and these techniques are also rather simple, so it doesn't have to be very complicated. You can use those techniques introduced before. All of them were rather simple approaches. Even the learning of a transformation matrix was just a perceptron network, right? So it's really not complicated. So people tried to make the model more complicated by restricting the resources available. For example, they said, okay, what happens if you only have 10, if your dictionary has only size 10, right? For example, the dictionary could be a very stupid dictionary that only says, well, a colon in German is the same as the colon in English, so and that's your dictionary. So you actually do not know much about German or English, or you don't have to know much about German and English. You don't have to know that cat and Katze are translations, but you only have to know the colon is the same in German and English. And it's easy to come up with such 10 word pairs. And the advantage of that is you can apply it to many more languages. So if you can solve it well with 10 word pairs, then of course you can get bilingual embedding spaces in many more languages than if you need 10,000, a dictionary of size 10,000, right? And the cool thing is, well, this literature that started out with doing word embedding estimation, bilingual word embedding estimation from 10 word pairs, then, well, it decreased down to 0 word pairs, having nothing at all. And then from then it went to doing machine translation without any parallel data. So that means, well, traditionally in machine translation you need examples of translations. You need to have a German sentence and the corresponding translated English sentence, right? Because most of machine learning and deep learning nowadays is still supervised, so you need to have these this parallel data. But with approaches that build on this unsupervised bilingual word embedding induction, we could also, people then also came to doing machine translation that doesn't use any parallel data. So the machine translation model does not know, does not any time see matched up sentences in two languages, but still can infer, can do machine translation, right? This is really, at the time that came out in 2018, this was really very surprising to the community. And to give you a little bit of idea how this works with only 10 word pairs, I will very briefly give an overview of this paper of Michael Artexter from 2017. So the main idea is, if we have a dictionary, right, we can get bilingual embeddings. We already know that because we know the approach of Mikolov, right? This 2013 here. So we know that if we have a dictionary, then, and of course we need to have monolingual corpus and monolingual embeddings. Okay, that's always the case. But if we have a dictionary, then we can get bilingual embeddings, right? So, and the other insight is, if we have bilingual embeddings, then we can get a dictionary, right? So why is that the case? Well, if we have these bilingual embeddings, then we know that, let's make an illustration here. Let's take this picture. Let's take this picture. If we have a bilingual embedding space where words across different languages are in the same space, then of course we can get a dictionary. To know what is the translation of eat, in German we check the nearest neighbors of eat, so it could be essen or trinken, and then depending which one is closer, we can take this as the translation. Well, in this case it would be trinken, but that's only because because the graph is maybe not fine-grained enough, or maybe it's an artifact of the picture here, right? But we can infer a dictionary from a bilingual space. So we could actually iterate this. We could start out with a dictionary, then we get bilingual embeddings. Having these bilingual embeddings, we can improve the dictionary. Having a better dictionary, we can get better bilingual embeddings, etc., etc. So we have an iterative formula, so to speak, and that's what they do exactly. So they use a seed lexicon. They use a small dictionary, a small lexicon, and this initial lexicon can be a seed lexicon. So it really can only contain, for example, corresponding punctuation across two languages, right? So this we can get more or less for free. Then we learn bilingual embeddings using the current lexicon. That's the Mikolov approach. And then we get a better lexicon from these bilingual embeddings, and then we iterate, right? So here's the illustration. So they have the initial dictionary, which says 1 and A, and 2 and B, and 3 and C are together. So we use this dictionary. To so this is language X, that's language Z. So we have, in language X we have the words 1, 2, 3, 4, 5. In language Z we have the words A, B, C, X, Y. We know the correspondences from our initial dictionary. Then we rotate the language X space by the transformation matrix. That's Mikolov method. And then once the space is rotated, once the X space is rotated and the Z space remains, of course, we can plug these two spaces together. They are now in a shared space, maybe not a very good shared space, but in an initial shared space. And we see that, okay, 1 and A here are together. That's what we already knew, but maybe now also X and 4 is together, right? So we already we get one more, and in this case we even get two more dictionary entries, and we put them back into our dictionary, and then we iterate, right? So this is really fascinating stuff.